All the previous talks are really impressive, so I'm a little bit nervous. So my talk is a little bit short, so I hope that helps keep it interesting. My presentation is negative bounds for avoiding conflict in implementing traits in Rust. I'm presenter is Yuki Okamoto from Japan. The overwork of our work is Rust has an interface mechanism called traits. When the same trait is implemented multiple times for the same type, a trait implementation conflict error occurs. This case often arises when programmers use the type parameters in their implementations. We propose a new construct and checking algorithm to avoid trait implementation conflicts in Rust. So let's get look at one by one. The programming language Rust provides traits which are similar to interfaces in Java. The name trait was originally proposed Scali in 2003, but in Rust, the system is almost the same as mixins and differs from the traits originally proposed by Scali. In this example, a new trait ID X is defined with copy and debug as its supertrait. And we can write method signatures and implementations within the braces. Traits can be implemented for types. In this example, the trait IDX is implemented for the type node ID. We can write method bodies in the implementation. In this example, we implement the index method. Methods can be called on objects of the type for which the method is implemented. Here, we say that the type for which the trait is implemented satisfies that trait. In this example, trait IDX is implemented for node ID. So we say node ID satisfies IDX. We can introduce type parameters in implementations. In this example, we introduce a type parameter T. Type parameters can require that some traits are implemented for them. These requirements are called trait bounds. In this example, the type parameter T has to satisfy both the old and copy traits. A trait implementation conflict occurs when the same trait is implemented multiple times for the same type. In this example, the trait IDX is implemented for the type T twice with different trait bounds. However, there can be a type that satisfies both clone and display. Therefore, these implementations conflict. For example, one type that satisfies both trait bounds is string. String satisfies both clone and display, so both implementation is implemented for string. But it is implemented for string twice. We found that there are multiple similar code segments in the standard library. For example, there is a from trait, which is used to implement type conversions. There are many from trait implementations for types that can be borrowed as the primitive string type. str is borrow of the primitive string type, and box str is a primitive string allocated on the heap. Call str is a primitive string with clone on write semantics. We assumed that these implementations could be unified into one implementation using the asRef trait, which represents types that can be used as references to a specified type. One of the reasons we cannot write this is trait implementation conflict. To address this problem, we added a minus operator to trait bounds. The meaning is to exclude types that satisfy the trait. In this example, string satisfies display, so the first implementation will not be applied to string, but the second one will be. There are several posts on web forums, such as Stack Overflow, asking how to resolve trait implementation conflicts. And most of the answers state that these conflicts cannot be resolved directly. Such conflicts typically arise when writing polymorphic trait implementations for related types. The suggested fixes in these posts often involve abandoning the use of traits or type parameters, which reduces code reusability. We expected that introducing negative bounds into the Rust language would reduce source code size and enhance method reusability. To discuss negative bounds, we define trait bounds and trait implementation conflicts. First, we think about the role of trait bounds. For a trait bound B, that trait bound requires all its ancestor traits and itself as AB. This and AB function A. And the trait bound requires all traits specified using the minus operator as neg B. In this example, neg clone minus display becomes a singleton set display. And A clone minus display collects clones ancestors and becomes a set consisting of clone and copy. Based on the role of trait bounds, we define trait implementation conflicts with negative bounds. For two implementations, a trait implementation conflict will occur when the unification between traits T1 and T2 and between E1 and E2 succeeds. With negative bounds, we additionally check the trait bounds. We have to check the trait bounds for type parameters that are bounded by them and are unified. We check the common part of the ancestor traits specified with plus and those specified with minus. If it is not an empty set, then we say that these implementations do not conflict. We implemented a prototype system in Rust to check implementation conflicts with negative bounds. We use non-parser combinator library to build parser. It has 8,068 lines. It is available at GitHub repository. Okay, so let me show a prototype. Okay, sorry. I would like to show this terminal display. Display.
I can't.
Okay.
Whatever this HDMI is connected to. I'm sorry.
I don't know. This.
Try that one.
Maybe not.
Yeah, it should be there.
Okay.
Okay. And then you can change the screen.
Oh.
Or, yes.
Okay. Thank you. Sorry for waiting. We implemented a prototype system, so we show a program that we will check. This program has IDX trait implement for type T that is bounded by clone trait, and IDX trait for T, it is bounded with display trait. Let's run. Yes, this two implementation is conflict since clone and display. There are types that clone trait and display both implemented clone and display traits. So I will rewrite this program. I will insert here to minus display trait and check. Okay. Now it's not conflict. Clone display, clone trait and display trait, but here display trait is specified with minus operator, so it is not conflict. Okay, so we assume that the computational complexity of checking trait implementation conflict with negative bounds is significantly larger than the current one. It's not significantly larger than current one. Our algorithm simply adds s n log to n, and we do not have to pay this cost if the unification fails, which will be the most common case. Our future work is to implement our algorithm in the chalk trait resolver to show that it is practical enough. We would also like to implement it in the next generation trait resolver that is currently under development. We will demonstrate that our algorithm works in practical time. We may also need to provide a formal proof of our algorithm. To show that our proposal is valuable enough, we will conduct a survey on GitHub. We have already found over 900 issues related to trait implementation conflicts by simply searching for related keywords on GitHub. There is still lot to do, so I will not run out of future work anytime soon. In summary, there is code duplication that can be reduced using negative bounds. We propose a new construct that includes negative bounds and a checking algorithm for them. We assume that the computational complexity of this algorithm does not increase significantly compared to the current one. Okay. Thank you for listening.
Okay, we have plenty of time for questions. If you have a question, please come up to the mic in the middle of the room.
Thank you for your talk. It was very exciting because I also looked at negative traits, was quite excited if anybody would start implementing them. Could you please go back to future work?
Future work? Okay.
Yes. Okay. So I'm curious, what is chalk trait resolver? And also, if I understand, you implemented your parser yourself. So why did you choose to do it this way? And why didn't you try to run it within some compilation stage? So why didn't you hack on compiler? So why did you make this choice? And what would be easier?
Okay. Chalk trait resolver is only trait resolver and not tied with compilers. So it is easy to implement our method, our algorithm into, and we do not implement our algorithm to compiler or chalk trait resolver. So now we simply implement check algorithm for simple subset of Rust. Okay.
Okay. So for quick implementation, and it was
yes.
Pretty quick.
Yes.
800 lines, not too much.
Yes.
Thank you for your talk. I have a question about so you try to resolve the trait error by adding a negative bound, right? So what do you think about the approach of like choose which trait to use for the function? For example, like if string has this trait for like two conflicting traits, what if like you can choose which trait to use, which implementation to use from the string side? Have you ever thought of that direction?
The method to choose?
Yeah.
Okay. We do not have any checked those algorithms, but we will do the task, so it is also future work.
Okay.
Please?
So I was asking, like, if this method has two traits to choose from, so you actually like added a negative bound to the trait side. Would it be also a good approach to add to choose which trait to use from the implementer's side?
Okay. So you said write types in trait bounds, or not? Maybe do you know specialization?
So I'm not really a Rust user, so
okay.
yeah.
Maybe specialization is one method for approaching the problem, but specialization select which type is most specific in those trait bounds, but it is not enough. We think it is not enough method, so because if there is two trait type parameters with trait bounds, it may occur that both the types, which satisfies both trait bounds, is still remains. We cannot select which trait bounds we should select. So we is this an answer?
Yeah. Okay. Thank you.
Okay. Thank
We
you.
can talk later too.
Okay.
Thank you so much for the great talk too. I enjoyed it. And I want to ask, why do you think that the Rust language doesn't support negative bounds already?
There is a discussion that whether that Rust should be implement negative bounds or not. And the conclusion is it's quite complex, and we will postpone the get result and implementation. So maybe it can be discussed more, but it is not discussed enough.
Okay.
It's okay.
Thank you.
Okay. Thank you.
Thank you for the talk. Very interesting, and assuming it works, very useful for Rust. So one question that kind of comes to mind is, how well or would your analysis work for a trait bound that is only negative traits? So your example, you had like display minus some other trait. What if you didn't have display? What if it was just minus trait? Would your analysis, would your algorithm still do anything there, or what would be the behavior?
Only negative bound. You said
if you only had the negative bound, you didn't have a positive bound associated with it. You only were saying not this trait. In many ways, it would almost be the universal set minus this trait.
Yes. Only minus.
Yes.
Yes. In our algorithm or in our syntax using implement this algorithm, it's not allowed to only minus trait bounds. So maybe it's okay. So maybe it is not problem with using only minus negative bounds, but we do not consider that at now.
Sure, that's fair, and I think that's a reasonable limitation to take on, because I've looked through some of those Rust forms before, and yeah, one of the main problems they always mention is that, okay, well, how do you decide the universal set minus things? So yeah, that makes sense to limit it. I was just curious. Thank you.
Thank you.
Thank you for your talk. It's very interesting. My understanding is that Rust has some limited form of negative trait bounds already, in the form that you can say that some type that explicitly does not implement, I think, sync, and send, those specific traits. I'm wondering, like, do these existing like sort of implementation have any impact on like the work that you've done here?
Maybe you said about old trait or something like that.
The send and sync traits. I think.
Thread safety.
Yes.
Maybe you said thread safety. We do not consider about that, so it should be added to future work.
Okay, thank you.
Thank you.
Is there time for one? So you also said that you want to formally prove that it's correct. So what would be your approach, and within which Rust formalization, if any, would you try to prove it?
We do not have any idea, but maybe we should provide. But in Rust, in practical, it is difficult to provide formal proof for entire Rust, full set of Rust. So maybe it's difficult. Maybe it can be. We can prove a small subset of Rust. We can provide we can provide formal proof for small subset of Rust, but maybe we have to implement it with large Rust full set, and next maybe its priority is low, but I would like to do, but no idea. So sorry, is the answer?
Yes.
Okay, thank you.